Hello everyone, we'll continue chapter 2. Now there are some examples in the lecture notes and in the book as well. Some electron configurations, and we know something that if an element is in a stable condition, that we call them inert or noble gases. So all the elements, they want to be in that state, so that's why they're going to share or lose or gain electrons to be in a stable configuration. So by default, noble gases are in a stable, which is, they finish it with P6 normally, and P6, all of them will finish with P6 basically. Those are the noble gases. They are, even helium is with S2 because it's filled here, there is no any electron to be given, so those are a stable condition, they call them. The other elements, they want to go to stable, so they will what? They will either lose or gain in order to be stable by the process of chemical reactions. We talk about periodic table, Mendeleev's, the way that his notes, how he was doing those things. And then this is the way that periodic table is gonna giving to us. Now, the first three groups that we have we said that this is S1, this is S2, this is D1. Those are willing to give up their electron. They're willing to give us their electrons and to be electropositive elements. Those are willing to give their electrons to be electropositive. For example, in this manner, we know that those are willing to give up their electrons. However, at the far ends on the right, which we have inert gases, they're all not going to give it. The other one we have the halogens, which is P. This is P5. This P5 and P4 is. What does it mean? In order to make this one stable, it needs 1, because it's P5. This is P5. So in order to make this one stable, we need to give 1 electron. In order to make this one stable, we need to give 2 electrons. It will be P6. It will be stable. Why? Because when we say stable, they want to be inert gases. They want to look like inert gases to be stable. So those will accept 1 electron, and this will accept 2 electrons. Let's call them electronegative elements. So they will having a minus ions, and this will be plus ions, which we call them cation and anions. We'll come back to them. We already know them. So those explanations are the inert gases basically filled. The rest of them, we know electronegativity. What does it mean? Electronegativity, how willing atoms are to accept electrons. For example, highly electronegative means that they need electrons. In the electropositivity means that also how badly they want to give their electron. And then they say a subshell with 1 electron, low electronegativity. This is subshell with 1 missing electron, high electronegativity. Why? Because you want to take that electron to fill its orbital. Well, metals, the electropositive, they give up their few electrons. This is something to gain a positive charge. We know that, for example, most of the elements, most of the metals, they will be positively, they will be cations or positive charges. Now with bonding energy and forces, we're not gonna detail them, just reviewed it. Now we know that a state of distance between the atom, basically it's the energy that we have it. If the atoms are close to each other, the force will be repulsion. So they will pull each other. When they're far from each other, there will be basically attraction. So the attraction, it's the potential energy when the distance, interatomic distance, are too far. There will be less potential, goes to 0 potential energy, because there is nothing to, you cannot attract 2 atoms far away from each other. There will be some attraction, but very low potential energy. However, when they're very close to each other, the repulsion, it's create a lot of potential energy. Why? Because they don't want to come to each other. They will just pull apart each other. So there is some part they call equilibrium, that basically they call them a stable condition, that those interatomic distance basically between the atoms will be in a way that they will be stable. They're not going to hit each other to pull each other apart. They're not going to love each other to pull, to push and to pull, it will be in a stable that they call equilibrium condition there. Now the force basically that is taking it, it depends on the energy. I mean whenever they are in a stable, there will be less force to pulling. I mean, it's if they are going far away from each other, the force that pulling them back together will be less. When they go close to each other, the force will be high to pull them apart. They call them repulsion and attraction. Repulsion means that they will go in this manner, they're pulling each other away, and this is gonna attract each other to each other, attracting toward each other. I mean, those are some calculation. We're not going to go into them, how to, I mean, the distance with using vector notations and the difference between the forces they're going to go. Another things that we may heard in chemistry, they called electron volt, which basically the measure of, we're going to use at least to explain the bonding strength, the electron volt, I mean the energy unit convenient for description of atomic bonding. We're going to use that one. I mean the energy that will be lost or gained by electron when it's taken through a potential difference of 1 volts. So if something happened when it's, for example, one electron is going from somewhere to somewhere, you are losing this electron volt or you're gaining this electron volt. So this is basically will be used to describe some energy, and those energy basically will describe some melting points, some other properties for the elements that we have. I mean 1 electron volt is basically 1.6 10 to the power minus 19 joule. We have it, just information. Now type of bonding that we have it. Now when it comes to type of bonding, we have 2 types of bond. They call them chemical bond, physical bond, or primary bond, secondary bond. So we basically chemical bonds, they call them primary bonding or chemical bonding. Physical bondings, they call them secondary bonding. I mean the name of it is clear that chemical bonding, I mean there will be interaction between the elements. I mean the 2 atoms will interact together, will share electron, and will chemically bond together. That we call them primary bond or chemical bond. However, secondary bonding or physical bonding, it's not something that chemically they will interact. We have some poles or dipoles, we call them, negative, positive. They will pull each other. I mean they will attract each other. This is going to be, they are together, they will be bonding together, but it's not chemically, they call them physically they will be bonding together, which we will cover them in different videos. So the type of bonding, primary bonding, they are strong, 1 to 10 electron volt, which is ionic, covalent, and metallics. Those are the type of bonding. We explained them, each of them in detail. I mean the secondary bonding that we have them, we have fluctuating induced dipoles, we have dipoles, permanent dipoles, we have polar molecular induced dipoles, we have some other, they call them London inclusion dipoles, and we have also another type, hydrogen bonds. So we're going to explain them in the textbook. I mean it's nicely represented in a textbook. We're going to follow those for the secondary bondings. Here they just put few of them, but in the textbook we have all of them, so we shall explain them on the textbook for much more details, at least to know them. So now what do I want from you to know from this ionic bonding? I mean mainly for us to understand that the properties. I told you that those are interatomic structure or atomic structure. We need to know some properties from them. Yes, we said that those are reviewed from chemistry, but we have to know them and we have to relate them to the properties that we have it. Now ionic bondings basically happens when the two elements, one of them highly electronegative, the other one high electropositive or low electronegativity, they're going to, one of them is willing to give up one of the electron and the other one is taking that electron, and this is basically they will be positively charged and negatively charged. They call them positive charge, they call them cations, and the negative charge they call them anions. And we have a table salt, or the salt that you're using it during your daily life. I mean the salt that you're using it is NaCl. I mean as I explained with this one, this is sodium chloride, the salt that we have it. Sodium has one electron at the outermost shell. It's valence electron 1. Look, one valence electron is willing to give it up just to lose it. I mean, in a chemical reaction, is going to lose this electron to what? To a chloride, which has 7 valence electron willing to take one more to be filled. So this basically will be ionic bonding. This one is giving it, the other one is taking it. It's fully, this guy is give it up. I mean, he's a generous guy. He has 1 electron. Well, you want it, I don't need it, have it. That's a simple way that they're trading. But there will be what? There will be friends together. They will work together. I mean, just because this guy gave something to the other one, and they will be basically best friend. So this will be a chemical reaction. Look, the metaphor, I'm just bringing it to understand how does it work. I mean, metaphor is nice to understand and to remember. I mean, that's why this guy is generous, is giving it up, and the other one is taking it. And there will be a chemical reaction between them, and this is going to give us this ionic bond here. Now there's many more that those ionic bonding will happen. Now in the ionic bond, I mean, there's a charge basically that's written here, I mean, they call this one non-directional. I mean, there's something that the ionic bond, I'm not sure if you heard about this one, non-directional. It means that in any direction, this is going to be useful. We're going to explain it in Chapter 8, in Chapter 3 as well. Non-directional, directional, what does it mean here? How does it help us here? Non-directional means that in any direction that you're looking at them, in any direction, there is attraction in any direction. I mean, if you look at this, let's just show you something else. I mean, let's just make it much clearer for us. Yes, this is NaCl. For example, they will be together. Yes, in any direction, this Na will be attracted to the other ones. I mean, and we call non-directional. So any direction, there will be attraction. There will be attraction to, because it's not gonna. These guys only gave up. For example, the electron, and the other one took it. So whether this one took it, this one took it, this one took it, it's basically we call non-directional. So in any direction you look at it, it's still we have the same attraction. This is in ionic bonding, we have it there, the ionic bonding there. Now what else I have to know on the ionic bonding, in the ionic bondings? I mean, this is what we call it here. I mean, we have 11 proton or electron. There is this one which is 3s1, and we know that this is the last outermost shell. Valence electron is 1. It's going to give it up. There will be what? Like this. So if I want to write Na plus, which is a cation, sodium cations, plus 1, it means that we're doing it for 10 electrons, because one of the electron is donating it, so 10 will be left. On the other hand, for example, chloride, for example, there's chlorine, we have 17, so it's 3p5 and willing to take 1. So when we be minus, chlorine minus 1, it means that it took 1, so it's going to be 3p6. Sometimes we're asking students, for example, to do the cations and anions electron configuration, and you're supposed to know that if there is plus, for example, if I write Fe plus 2, we know that there will be, we'll deduct 2 of the electrons, and then we do the electron configuration. We're going to remove 2 electrons. Why? Because plus 2 means that it donates 2 electrons, and then we do the electron configuration. Then what else we have to know about ionic bonding? There's something that it's for the ionic bonding. I mean, they are strong, but there's something we call them brittle. Now, any mechanical force, when it's trying to do this one, they're strongly resisting it, but they are brittle. Now, this brittleness is something important for us to know that. This brittleness is important to know. So when we know an element is preferring to have an ionic bonding, they will be strong, but they will have a property we call them brittle. Now, brittle properties basically means that it can easily break. I mean, not easily break, because they're strong, but the way they're failing, they will be brittle failure. I mean, not just easily broken, I mean, the brittle failure will be what? In a way they're failing, it is brittle. Well, it might not be clear what this brittle means for you, but in chapter 8 we explain this brittle failure. It's a fast failure. I mean, it's not going to give an indication to you. It's going to give you indication. You're applying force to them. It's very, very strong. Now imagine, let's say, a steel which is frozen. A steel which is frozen. I mean, there is a degree of you have to freeze it in order to make it brittle. Steel. This has happened in Russia. I don't know during which World War was it. They launched some of the ships. I mean, they were made out of steel. I mean, the calculation made somewhere. They didn't expect the temperature in Russia. Basically, when those ships went to, I mean, it's in the place is Russia. It happens there because the temperature is so low. Steel, which is normally bending easily, they call ductile. You can bend it easily. I mean, if you go out and you have a steel bar of a small diameter, if you try to bend it, you can bend it without even breaking it. Yes, you can bend. That's what we call ductile. It's reverse of brittle. We call ductile material. Now, in that time, the ship, which is in the cold area, steel, due to the temperature, what happened? The property changed. It became brittle. So what happens? Simply just broke. I mean, in the middle, the ship just simply broke in the middle, still without giving any indication, without even bending. So they made it with the experiment. They put the steel basically in a freezing temperature somewhere. I mean, there is a degree that it will change it to brittle. Take it out. Simply, if you bend it, it's not gonna bend. It's gonna break. This breaking is strong. It takes a lot of force to break it, but when you break it, suddenly break. They call this one brittle material. I mean, glass is brittle material. Glass is a brittle material. Why? Because it's not gonna bend. It simply fails. They call brittle failure. So this is an important information for us. So in order to know this one, we know what kind of properties we're expecting from those ionic bondings. Now, they said that there are some special cases, sure. I mean, there's nothing in chemistry to be true as once. There are always special cases. I don't know if you've seen NaCl single crystal. There's a video, I can share it to you. Basically, it's a Russian chemist. He's doing an experiment creating a single crystal. I mean, Na single crystal is creating a single crystal. I mean, they say this single crystal, if you put them inside water, imagine the salt that you have. They're they're small particles. If you give them an environment, they will simply, like all of them stick together and they will make a nice crystal structure. They call single structure. We will talk about single crystal later. In chapter 3, we'll talk about this single crystal as well. I mean, they say that it can bend without brittle. So they said that they have but they're underwater. Now this is gonna be like they called very strong non-directional bond. In any direction the bond is the same. Why? Because the Na basically goes compact the filling. So why some elements they prefer to go bond with the others? Because when they fill the gaps between the things and they will compact each other, this is gonna make them stronger and giving them some property. We're going to talk about this crystal structure in chapter 3. What is this crystal structure? We have them here. Now, I'm not going to go for those attraction and the repulsion forces there. Well, we're going to make another video on the covalent bonding to be short videos.